Hey everybody. So this is going to be a rough cut video, not ready for prime time, so it'll go in the unlisted bin on YouTube. But what we're going to do is get to know power series by way of an example, the geometric series. So here are the goals, hopefully. A lot of moving parts in this video. We're going to review some theory of power series because you've been looking at a lot of abstract, heavy theory about power series, and it's time to look at a concrete example. So we're going to do that, and we're going to see how it fits with the theory and try to take a step back and get a view of the big picture. So what's up with these power series? Where are we headed with these things? And then finally, one word of warning, there aren't any proofs. So I'm not going to try to justify a lot of this except to invoke the theory and show you how the theory works. So a big theme here is you want to think of a power series as a function. And so remember that given a power series, the set of x for which the series converges is some interval I that has one of the following forms. It has to be a very sort of special interval. So sort of the minimal case is that it's just zero. We know the power series converges when you plug in zero, but maybe it only converges when x equals zero and every other choice of x leads to a divergent series. That's sort of a catastrophe from the standpoint of convergence. So that's one possibility. The other end of the spectrum is that no matter what you choose, the series converges. So in this case, your interval would be the whole real axis. So that's another possibility. In many ways, the most interesting case is that there is some positive number r for which there's an interval with endpoints at negative r and r, inside of which you get convergence, outside of which you get divergence, and then at the endpoints themselves, you can get all sorts of behavior. It's perhaps the case that the series converges at both endpoints, so you'd have a closed interval of convergence. Or maybe you converge only at the right endpoint, or maybe only at the left endpoint, so you'd have a sort of semi-closed or semi-open interval. Maybe you don't converge at either endpoint. You get divergence in both cases, so you would have an open interval of convergence from negative r to r. But in any case, these are sort of the four types of finite intervals you could have. And I'm going to paint both of these endpoints gray to sort of denote the ambiguity. And we will say in this case that the radius of convergence is r. In other words, if you start at the center of the interval 0 and you march out r units, you get to the edge of the interval. And this is sort of a one-dimensional analog of what you'd have with a disk, right? You start at the center and you march out r units and you're at the boundary. I mean, so that's sort of the motivation for saying that this is the radius of convergence. Now, to be consistent, it's pretty clear what we should say in the other two cases, right? So in this catastrophic case of almost no convergence, you want to say the radius of convergence is 0 because you don't go anywhere. 0 is the only place. And then in the other case here, the maximal case, you want to say the radius of convergence is infinity because you can go as far as you want from the origin and you're going to be able to converge. So in all cases, we can talk about the radius of convergence. Okay. So what's going on here? So this power series defines a function with the domain I, the interval of convergence, because clearly for any x inside the interval of convergence, you plug it in, you're going to get a number. So let's just define this function. Let's call it f for a moment. F of x is equal to the value of this power series whenever you plug in something in the interval of convergence. And here's sort of another part of the theory you learned. This function is really well behaved. You can find its derivative and its antiderivative. And the way you would do it is just like you would hope. You just take this power series and you either differentiate term by term or you integrate term by term. Notice the constant of integration, because when you integrate, you can have a constant involved. Now, there's a little funny notation on the side here. Please note that I've used a little subscript with a little sort of degree marker for open. It's the open interval of convergence on which you know these are true. The theory doesn't tell you generally if these things continue to hold at the endpoints. They might or they might not. It would always have to be a case-by-case basis where you test out to see if it's true. Okay, so we've reviewed the theory, and now it's time for an example. It's time to get down to brass tacks. And we're going to go right back to the geometric series. So way back when, we learned that this series on the left converges to the value 1 over 1 minus x when the absolute value of x is less than 1. Well, take a look at this now in the context of what we've been learning lately. This is a power series, and that is its interval of convergence. It's, absolute value of x is less than 1 is exactly what you need for this series to converge. That's all x between negative 1 and 1. And by the way, this is an explicit formula for the value of the function defined by the power series. So we actually know what it converges to. It's 1 over 1 minus x. So let's rewrite all of this a different way. We're going to say 1 over 1 minus x is equal to the value of this power series for all x in the interval of convergence. Okay. Now, here's one way to think about it. We could have defined a function f by this power series. And then someone could have said, wait a minute, but we know what the power series does. It converges to 1 over 1 minus x. And so you'd say, oh, okay, well, if we had defined a function this way, then we'd have to conclude that actually that function is the function 1 over 1 minus x. So here's another way of looking at it. You could say, look, this function, 1 over 1 minus x, is represented by the power series on the interval of convergence. So its values could be described as the limiting value of a power series for all those x. So this is language we'll use. We'll talk about finding representations of a power series or representatives on an interval. And that leads us to two kinds of games we're going to be playing in the future. So here's one kind of game. You start with one of your favorite functions. So, you take the exponential, arctangent, cosine, some complicated function derived from all the, functions you see in pre-calculus. And given one of these functions, you could say, look, let's find a power series that represents the values of those functions. That's one kind of game you could play. Here's another kind of game. You could start with a power series. And you can say, okay, here's a power series. You tell me what the explicit formula for the function is for that series. So in our example we just looked at, we started with this power series, and you'd say, hey, that's geometric. I know what it converges to. It's 1 over 1 minus x. So here's an example of that game where you start with a power series. You're like, okay, what function does that define? Okay, now here's the scoop. This game at the top is relatively easy. Okay, turns out that you can sort of win this game. And in fact, there's a winning strategy. It's called the theory of Taylor series. And for most functions, all the ones we see in pre-calculus, this theory is going to allow us to algorithmically find the power series that represents the function. So when I say algorithmically, I mean it's like a bread machine, right? You just dump in the ingredients, turn it on, and it'll produce your product, and it'll be your power series. So this game's relatively easy. Now, it turns out this game is relatively hard. In fact, I would say that sort of generically, it's impossible. If you wrote down a random power series, chances are 0 you're going to be able to figure out what it converges to. So it's rather a miracle that the first example we looked at was an example of starting with a series and then finding its value. That's how special the geometric series is. But anyway, let's go back to this example. And now I don't want to play either kind of game. I just want to play. I'm going to play with the theory and just see where it leads us. So the theory tells us that we could differentiate a power series function term by term. And by the way, we know how to differentiate this. So if we differentiate both sides, we're going to get a new relationship. So what's the derivative of 1 over 1 minus x? Let's write 1 over 1 minus x as 1 minus x to the negative 1. So the derivative would be, we'll do the power rule, exponent's negative 2, the negative 1 pops out. Oh, and negative 1 because of the chain rule, right? And those cancel. So this function just turns out to be 1 over 1 minus x squared. So that's what the derivative of the left side is. But if you take the derivative of the right side, we can just go term by term. You're going to get 0 plus 1 plus 2x plus x cubed, 3x squared, and so on. So there is our power series. We took the derivative of both sides. And remember that the theory tells us that the new equation you get is only guaranteed to hold on the open interval of convergence. So we started with the interval of convergence was already open from negative 1 to 1. So guess what? This thing has to be true on negative 1 to 1. And it might be true also at the endpoints, but you have to check on a case by case. So generally you can't just assume that this is true at either endpoint. You'd want to test to see if it's true. So let's do that in this example, just to give you a sense of what that would look like. You'd say, okay, what happens at one endpoint here when x equals 1? Well, that power series diverges to infinity. And when x equals negative 1, you get another weird power series where, okay, that doesn't diverge to either negative infinity or infinity, but it definitely diverges because just try to play around with the partial sums there. You get 1, negative 1, then you get 2, negative 2, then you get 3, negative 3, and so on. So those partial sums don't go anywhere. They just sort of wobble and explode in magnitude, and that series diverges. Okay, since the series diverges at both endpoints, well, you can't possibly, these inequalities have to remain strict. We can't possibly claim that they're going to be true at equals, right? X equals negative 1 or 1, because the right side diverges, so that can't happen. But you know what? There's something else besides that should have told us that this wasn't going to happen. So remember, one of the components of the theory is that when you take the term-by-term derivative, you might lose convergence at the endpoints, okay? You can't pick up convergence. You can only lose convergence. And because of that, well, we didn't have convergence in the first place. And because we didn't have convergence in the first place, when we took the derivative, there's no way of picking it up. So the theory already told us there was no hope of convergence at the endpoints. I mean, we just verified it by brute force, but here we can see that the theory told us that there wasn't a chance anyway. All right, so let's play the other possible game. We could anti-differentiate. So the theory tells us we can anti-differentiate term by term. And of course, we know how to do that to the left side as well. So let's play the same game. What is the antiderivative of 1 over 1 minus x? It's a logarithm. Well, you know, got a constant of integration there, and make sure that you put your minus sign in there because the chain rule is going to spit out a factor of -1 when you actually take the derivative. So this should be negative ln of 1 minus x. Okay, so now what? We know that the antiderivative on this side is this, and where'd the constant of integration go? We're just going to put it on the other side in a moment here. So we're going to take the antiderivative term by term. So you get these. Make sure you can run the power rule in reverse. And there's our constant of integration. So here's our relationship. But now, here's the thing. This is a lot like when we played with differential equations. It's a lot like an initial value problem because actually, we want these two sides to be equal for all values of x. So we can actually go in and plug in a value of x and figure out what x has to be. And so when you plug in 0, you see that the left side has to be negative ln of 1. That's just 0. And obviously, if you plug in 0 to the right side, you're going to get just k. And so what do we conclude from this? Well, that constant of integration, actually we have to make it 0 to make both sides equal. And when you do that, now you have your power series representation for negative ln of 1 minus x. So let's see, what about an interval of convergence? Well, once again, the open interval of convergence was -1 to 1, so we're going to keep that. And then the issue is, did we pick up anything when we integrated? So before we explore that issue, let's remind ourselves that if there's a -1 in front of a logarithm, you can bring it up as an exponent inside. So actually, this might look prettier as ln of the reciprocal of 1 minus x. So we're going to make that change real quick. So here's ln of 1 over 1 minus x. All right, so now the theory says that we might have picked up some convergence at the endpoint. So let's test that directly. When x equals 1, well, you get the divergent harmonic series, no chance, so we didn't pick up convergence at 1. How about -1? Well, actually, when you plug in -1 to the series, you get the opposite of the alternating harmonic series. Just carefully plug in -1, and you'll see that those terms alternate. And you can prove this converges by the AST, or you can factor out a scalar factor of -1, and you just get the alternating harmonic series, which you know converges, but in any event, that converges. So we actually did pick up convergence at the endpoint -1. But it's a far subtler issue to say that the two sides of the equation have to be the same. So we know the series converges when x equals -1, and you know that you can plug in -1 into that function on the left because it is in the domain. But since this happens at the endpoint, it's a rather delicate issue to say that they're the same, but I'm going to invoke a little bit of theory. It's an advanced theorem that asserts that in this case, the function value will in fact match the value of the series. So it turns out that when you plug in -1 to both sides, it's still going to be true that these are equal. Let's just run with this fact. I won't even attempt to prove it. It's called Abel's theorem. But here we go. So notice the subtle difference here. I've now claimed that both sides are equal, including the case where x equals -1. Okay? Now, if that's true, watch what happens when you plug in -1. You get this series on the right. You get ln of 1/2 on the left side. ln of 1/2, that's the same as negative ln of 2. And if you multiply both sides by -1, you get this. And that should look familiar. We saw that earlier. We had no reason to understand why this was happening, but now we have a very good reason. We can sort of see why it's happening. Somehow this series is related to the logarithm function through the theory that we were just looking at. So I hope this example gives you a taste of why power series manipulations can actually be really kind of fun and cool and even somewhat magical. And we're going to spend a lot of the next few weeks really trying to understand examples and the theory behind this. We're going to learn that rule, the Taylor recipe that allows us to find the power series representation for any reasonable function. So all this is sort of upcoming, and so I hope we have some fun with that.